Hi guys, nice to meet you here. My name is Mike and I'm doing engineering for Fluence Labs. And today I'm going to tell you about Fluence Compute Engine that intended to run multimodal WebAssembly applications with help of interface types. So I will pronounce this like FCE. In particular, the agenda today is follows. So first of all, I will talk a little bit about the Fluence architecture, what we are doing and how. Then I will also talk a little bit about WebAssembly and especially about interface types proposal. I believe that many of you know a lot about WebAssembly, but I will just highlight several important points that are needed for other part of this talk. And then we will talk a lot about the Fluence SDK and the architecture of FCE. And at the end, we will talk why, in my opinion and in the opinion of our team, Rust is one of the most suitable languages for any projects using WebAssembly. So let's move on and start with the Fluence overview. So Fluence is a decentralized function service that intended to run WebAssembly modules with several important features. So the first one is zero DevOps. That means that all DevOps is done by the Fluence network and Fluence nodes itself. The next one is a easiest integration with other modules with help of interface types. And the last one is a special language called Aquamarine that provide a way to run complex multi-agent request scenarios across the Fluence network in the easiest way. And I hope that we hope that in the future Fluence will allow developers to get paid automatically for distinct modules or entire application by the royalty model. Here, the royalty model means that developers will get paid by the fact that their applications or modules are used by anyone in the Fluence network. And on this slide, you can see the general overview of the Fluence network. There are several important terms here. The first one is a module. So module is a piece of code that compiled to WebAssembly with special API. So I will talk a lot about this API in the section devoted to the Rust SDK. And a bunch of modules can form an entity called service. So service can be considered like a program or like an application. In its turn, several services can form a backend. And the last one is a function. So function is a piece of code written on Aquamarine that can communicate with each services that form this backend, and this function is live on this backend level. And it's important to know that each service here could be located on a separated node, a separated peer in the Fluence network. And from user point of view, these backends could be seen like API. This function could be seen like an API of this backend. So like a general function as a service. On the slide, you can see example of Fluence Aquamarine script. This one is a chat. Yes, so Aquamarine is based on pcalculus. So, but actually, I won't talk much about Aquamarine on the slide. If you want to know more, you have special launch event on the beginning of November. So if you want to know more, please follow us on Twitter and you can find the link of this event. So let's move on to WebAssembly and interface types. I super love this slide from Ben Smith talk from CPPCon last year. You can find it by this link. And there is a directed graph, and moving from left to right, you can construct your own application of what is WebAssembly. I ended with this one, and here maybe the most important feature, or maybe the most important limitation of WebAssembly, is that WebAssembly supports only primitive types. So there are only 4 or 5 integer or floating point types, and so primitive here means that there are no any arrays, strings, structures, enums, or so on. So only just integers or floating points. And on this slide, you can see life cycle of WebAssembly application. And the WebAssembly module here could be considered like a black box. So black box here means that it can't use any operation system servers, for example, like syscalls, yes, except only with imports. So imports specify which services of browser or of WebAssembly standalone runtime can be used by this module. Yes, an export uh, provides a way to communicate and to call functions from WebAssembly module from host. Yes, host here is also, for example, browser or standalone WebAssembly runtime. Another gem from WebAssembly world is Wasm. WASI stands for WebAssembly System Interface, so it's standard for imports. It provides several, about 50 imports that looks like a POSIX-like imports. So here you can see some of them. Some more information can be found in the docs. So, and the main purpose of them is to provide a standard way uh, to form this import section of the WebAssembly binary. For example, if you have the simple application that just print hello world to the console, yes, and if you compile it with Wasm32 WASI target, you can obtain these 5 imports in your import section in the resulted binary. On the slide, you can see some of several WebAssembly runtimes. Actually, there could be divided into browsers like SpiderMonkey or V8 and to server-side type, yes. The most famous ones from the server side is WAVM. It's written on C++ and it is a reference implementation. The next two, Wasmer and Wasm, they're written on Rust and support several compiler backends like Renleaf, Single Pass, Lightbeam, and LVM. And the last one, maybe is the most interesting one, in my opinion, because it compiles WebAssembly to a JVM. So it translates each WebAssembly module to JVM class, and it's written on Kotlin. Here we can see a complex scheme, how interface types looks like. But maybe the most important takeaway here is that on the center of this picture, there is a WebAssembly module. This WebAssembly module operates only primitive types, yes, only integers or floating points. And this module is wrapped by adapted module, yes. Here wrapped means that for every import and every export in this raw module, in this WebAssembly module, there could be corresponding adapter, yes, adapter import or adapter export. And the main purpose of this adapter is just to lowering or lifting types, yes. For example, export adapter aims to lowering type from interface types from complex types like strings, arrays, and so on, to primitive types, to integers and floating points. And in its turn, import adapter is just to lifting values up, yes, and just provide a way how raw values can be converted to interface types, yes, to strings, arrays, records, and so on. And other takeaways from the slide that Wasm in binary format is divided into sections. Yes, and there is a special section called custom section, and the section in the section could be located any user-defined format, any user-defined byte array, and actually interface types should be located on this one, yes, on this section. Also, it's important to know that this interface types proposal adds several instructions. Yes, this instructions aims just to lowering and lifting types as an adapter. Yes, and for example, you can't write program with these types yes, but it's important to know that there are several new instructions that should be called and that should be interpreted, or for example compiled, and I will show later how they look like. So let's move on, and on the slide you can see current state of interface types. So actually it is on the feature proposal state. So it's just a level 1 of fifths. Yes, it's the first one from now to 0, or sorry, from 0 to fifths. And actually, if you look at the interface types repository, so it's this one, you can see that there wasn't updates for a long time. And the newest one, the newest version, actually is on the linking branch. And about 2 weeks ago, there was a pull request from this branch, and you can see the newest version and the newest explainer of interface types in this pull request by this link. As far as we know, interface types aren't used anywhere for server-side applications. Maybe only Wasm engine support it now, support generation of WebAssembly binary. But as far as I know, it's only useful for Wasm engine, for Wasm time. It dropped support in its turn, so there are no server-side applications that using interface types now. And it's said, but on the current stage, on the current on the master of the interface types, yes, they can be used out of the box, yes. And later I will show why. And actually, Wasmer and Wasm time has support, but only partially support. So Wasmer supported by separate virtual machine agnostic rate. You can find it by this link. But to integrate it with Wasmer or Wasm time, you need to do a lot of work. And Wasm time dropped support of interface type on March this year. And you can see discussion about integration interface types by this in this issue by this link. So now interface types first of all can be used out of the box without this pull request. Yes, I mean this one. And also there are no support in runtimes for interface types. So let's move on to the Fluence Rust SDK. And when we start to develop it, we ended with such requirements. So first of all, we want to make our SDK the most convenient for users. And actually, we thought that it would be good if this SDK would be similar to something familiar. For example, Wasm engine. Yes, Wasm engine may be the most important and the most known gem from the WebAssembly world, especially from Rust integration. And the last one is the last requirement is the most easy way to port existing projects, existing applications to Fluence. So, and actually, we tried to port Wasm engine to our ecosystem, but we failed because there are a lot of really a lot of code that needed only to support JavaScript in Wasm engine. So we ended with our own SDK that I will show you later. So despite all limitations, despite that interface types only on the early stage now, and they aren't supported by a variety of WebAssembly runtimes, but interface types allow you to write on vanilla Rust. Here, by vanilla Rust, I mean that you can use all, not all actually, but several high-level types like strings, like structs, and so on. So, and the only thing that you need to do is just to wrap your function with procedure macro. Here you can see this procedure macro, FCE. So, and this means that this function, greeting, will be exported from the WebAssembly module. So the full example of whole world you can find by this link. And here are also several examples on the examples on the master. So maybe the most important feature of FCE is multimodal scheme with shared nothing linking. Actually, there are two types of linking scheme in WebAssembly world. So the first one is sharing nothing, and the next one is shared everything. So in shared everything, a module can share everything, yes, like memory, like table, and so on. In shared nothing, the only thing that can be shared and can be linked between modules is only import and export. And here you can see scheme when one module linked to other module only by corresponding imports and exports. So, and the scheme, the only scheme that is that FCE support now. So how is this all look like? So here we can see a piece of code from 3 modules: site storage, curl, and local storage. So in all this example is just example to download and save sites, yes, by URL. So here you can see what you need to do to link modules together. So the only thing that you need to do is also only just to wrap your foreign mode declaration, foreign external block with our procedure macro, with FCE. And in this block, you can use all types that are currently supported by our SDK. So strings, vectors, and so on. So I will show you later. And call here is a standard call of foreign functions interface. Yes, like in general in Rust. So here we just call it like itself. Yes, like a curl with string argument. So this is, for example, also can be found by this link. Also, our SDK supports parsing structures, and the only thing that you need to do is also just to wrap structure with FCE macro. And after doing this, you can use this type as an argument or as an output type. Also, it could be used in a foreign mode or in exported functions. So it used like in vanilla, like in general Rust. So you shouldn't think how this should transmit between modules. Yes, you can just type like in vanilla Rust, and it's all works. So actually, to support this and having a fact that interface types requires using custom sections. So I mean here that after producing a binary, this WebAssembly binary should have custom sections with all adapters, yes, with all interface instructions, some mappings, and so on. So, and here for us is a complex task now because procedure macros aren't stateful, yes, and moreover, their order of applying isn't defined. And to achieve this, to produce WebAssembly binary with a custom section, we use two-stage scheme. Yes, sorry. So the scheme is exactly like Wasm engine is used. So on the first stage, we expanding macro, and in expanding macro, we generate several custom sections that has all necessary information for the second stage. And on the second stage, we generating interface types. So let's consider this example with hello world, or sorry, with greeting function. So on the first stage, this macro is unwrapped to this form. And here you can see that the special global is generated. It's located on the custom section that was dropped on the second stage. And on the second stage, with help of this section, interface types in custom section is generated. And then the section is cut off from the resultant binary. Yes, and all of this work is done by our special CLI utility called FCE also. Yes, you can install it by cargo install FCLI. So you can just use it like FCE build, and also several cargo flags also supported. For example, you can write FCE build release, and the release binary will be compiled. In our SDK, we support now only the following types. So actually, there are all integer types, all floating point types, string, vectors, and structs. And also, it's important that unlike Wasm engine, we support vectors of any types inside this type parameter. For example, you can use you can form your argument like this one. Yes, you can use array of some struct that also has vectors inside. Yes, and you can return vector. And this form you can use both in imports and both in exports. But of course, we have things to do. We are working to support enums and to support box types like box, arc, RC, and so on, like Wasm engine do. And now we have limitations that we support passing only by reference. Oh, sorry, by value. So we now support only passing by value, and we are working all to support passing by reference. So let's move on to the Fluence Compute Engine architecture. Generally, it looks like this. It looks like three layers, and on the first layers there is engine, yes, that support the so-called role operations. Then it's Fluence function as a service, so it's intended to run function as a service tasks in our network. And here two services, application services that means services that we are seeing on the third slide, and Aquamarine. So this architecture aims to fit different purposes. So first one is running services, and the second one is running Aquamarine. And so we done it in this way to use it to help other people to integrate it in another scenarios. For example, we believe that such plugin architecture, such layered architecture could be useful, for example, in tasks like gaming, for example. For example, if you want to write a game that supports several plugins or several modules that should encapsulate its states itself, so you can use for this task FCE. So you can compile to FCE to WebAssembly and then load WebAssembly modules inside your games. So let's consider each layer. From on this role layer, on this engine layer, you can see this API. So there are several functions. The first one is the load module. Yes, this function receive Wasm byte. So just a byte that form a WebAssembly module. So it's loaded inside FCE by name and with special configuration, as that is represented by this argument. Also, of course, you can unload your module by name. Then you can get a WASI state of your module. So WASI state here is from Wasm crate. This WASI state contains, for example, all environment variables that mapped to your binary, and for example, also all file system inodes that are used now by your module inside FCE. So the other one is the interface. So this interface returns all exported functions by this module. Yes, this is a special structure here, FCE function signature. So it return all names. Yes, we support names and types of arguments and the type of output value. And of course, you can call a module by module name, and you can call function inside this module, yes, referenced by this module name, and the special arguments. And here you can see type iValue. So iValue here stands for enum that combines several iValue types like strings, vectors, arrays that you can see here. Yes. So on the next level, we have function service. They combines they has a lot of variants of instantiation. So say it has a lot of constructors. So its main purpose is just to prepare function service, works with config, parse JSON, and also work with host imports. So we'll talk about host imports later. And on the last layer, we have service runtimes. So the first one is app service. So it sets several WASI environment variables and prepares directory structure for Fluence service. And Aquamarine VM is so actually I didn't say that Aquamarine is also compiled to WebAssembly. So all this pcalco script is compiled to so-called Aquamarine intermediate representation, and in itself, this intermediate representation is also compiled to WebAssembly. And to support and to provide some easy way to integrate, we have Aquamarine virtual machine on this layer. So just plug it in the Fluence node. And all of this layer can be found in our repository by this name, yes, in these brackets. On the slide, you can see the example of the service configuration. So service configuration consists of modules. Yes, here you can see 3 modules here. On module, you could configure, of course, name. And here the option means that configure the maximum memory that can be used inside FCE for such model. And also for each model, WASI state could be configured. So here you can see 2 options, pre-open files and mapped dirs. So the first one is the array of files that can be accessed by this module. Yes, this works like a sandbox, and the module could access only files from this list. And also you can map these files, pre-open files, to some handy alias, like in this example. Another example, another option is a mounted binaries. So mounted binaries is a special binary that translate all code to the corresponding CLI. So for example, this one provides you a function named curl that has one argument with string type and output type also of string type. So when you call curl with a string, so the string is passed to this CLI module, yes, referenced by this pass, and the output of it is also passed back as the output of a curl function. So this neat because not every program every application could be compiled to WebAssembly. For example, some complex application like databases, like MariaDB, like Oracle, or something like that, can be compiled to WebAssembly in efficient way. Moreover, WASI isn't support now such features like sockets, or, for example, API for asynchronous programming, and some operation system services also. So in here is a way to work with such binaries, such programs that can be compiled to WebAssembly. So in future, when WASI support Unix circuit, we will use Unix circuit instead for applications that support Unix circuits, so like database and so on. So the complete example of the server's configuration can be found by this link. So let's dig a little bit into details and see how multimodal cores works in FCE. So let's consider again our three module: site storage, curl, and local storage. And so site storage imports three functions, one from curl and two from local storage. And for each function, there is a corresponding adapter, corresponding import or export adapters from the interface types world. Yes. And actually, the linking is done between these adapters. And inside each adapter, there is an interpreter. So interpreter is a separated standalone virtual machine that work like interpreter, yes, and it interpret adapter instructions one by one with real stack. So, and this interpreter aims to learn or leave types between interface and role types. So let's see the example. Let's see how interaction between function curl works. Yes, so let's imagine that site storage module invoke curl from the curl module. Yes, so here you can see prologue of import adapter for curl function. So, and this adapter is located inside this adapter import. Yes, so this one located here. So, and here you can see four instructions, interface types instructions. The main purpose, here you can see arget. So it's instruction copy from inputs values referenced by this index to the stack, to interpreter stack. This one, lift memory. So as you can see, it lift memory. It lift from these two values. It means, so the first one means pointer to string, and next one stands for size of the string. So lift memory consumes two values from stack, pointer and size, and produce string, UTF based string. And then code export adapter. So this one is an import. Yes, it's an import of this site storage module. So let's see what is done next. So, and here we now in this export interpreter. And so there is, we need to learn, yes, we need to learn back high level string inside role types. So how it should be done? Here we also have arget 0. It copies value from parameters, from arguments to a stack. Then this one computes size of string, yes, and consumes this string from the stack, and push back to the stack string size. Then we call allocate. So this allocate is ABI, yes, of this each instance in our FCE. So this allocates memory inside corresponding instance memory. So in here we allocate memory the size that is produced by these instructions, by the string size. And then we need to warn memory back. We need to warn string back. Yes, and this instruction takes two values from stack. The first one is a pointer inside Wasm instance, and the next argument is a string itself. So in here we need to copy again string from arguments to interpreter stack, and then call lower memory. And only then we call curl. So this is essential curl from this instance. So in here only here we call this one. So let's see what we should do next. Next, we need to leave memory. Yes, we need to extract memory from this instance and pass it back here. Yes, pass back to this import adapter. But here we have a problem. This problem in false. So to here we need to warn this memory back. We need to warn it to this string back to the memory of this Wasm instance. To do this, we need to execute instructions similar to this one. Yes, we need to call string size. We need to call string lower memory. So, and the problem here in false. So actually, each of these instruction consumes string from the stack. Yes, but on this interface type proposal, we we do not have instructions for duplicate or for swapping values on the stack. So, and to make this scheme work, we have to add these instructions. We have to add duplicate and swap instructions. So in here we just duplicate strings that returned by this export adapter inside the interpreter stack of this import adapter, and then and only then we can done all this. We can do all the separations. Yes, to warn string back inside this Wasm instance. So in this how interaction between these two modules work. Yes. So here you can see that there is some overhead between modules because first of all we need to lift memory, then warn, then lift back, and then warn back. So the other important point is the host functions. So host functions is a function that exported from host, yes, for example, from browser or WebAssembly runtime to WebAssembly module. But how this function can be exported in the most easy way? Yes, we found this one. So there is a host import descriptor inside FCE that can be passed to FCE at the construction stage. And this descriptor contains several fields. The first one is a closure. Yes, this closure contains, this closure has such type. So here you can see that we pass context. Context here stands for Wasm context. And with help of this argument, some internals details can be accessed. Or for example, you can mutate memory directly, or you can access tables and so on. And the most important argument, so the second one is a vector of I values. So this I values that enum for interface type values, and here is passed by value to this closure, and this closure return back option of I value. So it seems easy. Yes, it seems self-description. You can just uh, obtain vector of I values and should produce option of I value. So, and here also you should specify uh, argument types and output types. These fields are needed only to link this closure to Wasmer module. Yes. And last one is a error handler that will be called if lifting values uh, failed. Yes. So it is the um, last way to do some cleanup, or for example, to produce some other default I values in case of fail. So on the slide, you can see example of REPL. We have a special CLI utility called REPL that intended to test service application. So, and this REPL provide a way to load modules, yes, to load, unload, call, and done all work that you can see on previous slides where there was architecture. So, and it works like this. For example, if you load IPFS node, so we have such servers in examples. You can find it in FCE repository. So, and if you load it by this command, yes, just by providing config as argument of FCE REPL. So here you can see, for example, you can type interface, and so the service consists of two models, IPFS effector and IPFS pure. And IPFS pure is a model that really should be called from the external world. And it's just an example, and they are linked together. So, for example, put linked to this put, get to this get. And by this way, you can call IPFS pure. So, and here we put inside IPFS array of three elements of 1, 2, and 3. Yes, so its arguments could be passed in JSON, in this JSON string. So, and here we can see some work how IPFS that also mounted inside this IPFS effector module by mounted binary option. Yes, and the result here is this string, is a hash, is a multi-hash of this array that now located inside IPFS. And then if you pass this string, this multi-hash inside get, you can obtain back this element, this arrays of three elements. What about Red Hat, and what about how fast is this? Yes. So we have ported Redis, and the Redis is about half of megabytes in optimized way. And here you can see so that to load Redis inside FCE. So load here means that Redis will be compiled as from WebAssembly to native by ahead of time compiler by CleanLift here, and all imports and exports will be instantiated here with interface types, with interpreter, and so on. So, and time here is only just a half of second, less than half of second. I tested it on my MacBook Pro, so just like this. And here you can see example of calling function inside Redis. We have partially lazy linking scheme, and the first call is the longest one. So here you can see that about 3 milliseconds, but the next one is about 64 microseconds. Yes, it's in my show this mu isn't printed well. So it looks not so slow. Yes. Uh, in the future, we have several plans. Yes. First of all, we want to support sharing everything linking scheme. Then we planning to support full lazy linking. So this lazy linking will provide ability to load modules that currently don't have um, providers for imports. For example, if module A has import from module B and B has import from module A, they can be loaded inside FCE now. Yes, because there is cyclic references, and to load A you need B, and to load B you need A, so it isn't possible now. And to make this scheme work, we need full lazy linking scheme. Also, of course, we want to support more argument types inside Rust SDK. As I already mentioned it, yes, we want to support boxed types and passing by reference. Also, we make it virtual machine agnostic. We now heavily depends on Wasm. And finally, we want to support multi-values that aren't supported now by our interface types and our SDK. So let's move on to our last section, why, in our opinion, Rust is one of the most useful languages for WebAssembly. So, in our opinion, there are several points, yes, and maybe the most important one that all targets, so all targets here means Wasm32 unknown and Wasm32 WASI, and also I missed here Wasm32 EM scripting. Yes, and all of them are supported out of the box. Yes, you can just install it in one CLI command. Yes, and it's the most easy way how it could be obtained, comparing with C++, for example. Uh, so the second feature is the support of procedural macros. So all the power of procedural macros provide the ways where you can just wrap function structure of foreign mode with just a macro, and all will be work. Yes, and for example, it isn't possible in C++. In C++, you can't generate huge meta information in a way how you can do it in Rust. Yes, third one is a good ecosystem. There are a lot of libraries, there are a lot of examples. So there are a lot of people that can help you. So, and also modern amenities. That means that there are a lot of tools, also a um, lot of activity communities in the world. So here I think that you believe that Rust is one of the most suitable languages for any projects that relate to WebAssembly. For example, mm, if you if you use Wasm32 unknown target, and for example, you can compile some huge application that depends on, for example, on Mutex, for example. But on MVP, WebAssembly is only single-threaded, and because of this, Mutex could be represented just by a Boolean, or here it's, as I remember, it's cell. So yes, it's only one variable is enough. Yes, and atomics and Mutex aren't needed here, so we just log here is just translated to these ones. So it's very simple. It's very easy to use. For example, in C++, if you try to use a log from Mutex with this target, so there will be import from environment model to log, unlog, and so on. Also, this target support DLmalloc-based allocator out of the box. So there also won't be any exports from, for example, with malloc free or so on. So this code will be compiled inside the WebAssembly module. Uh, So the second target is a Wasm 32 WASI. So it, as I already mentioned, a transformal import to WASI-like import. And in my opinion, in Rust, it allows to compile a variety of applications, yes, with operation system interaction, with help of Wasm engine, and also with browser interaction to WebAssembly. So it just uh, transform your APIs that are used to interact with operation system, just transform it to that POSIX likes imports, and all will works on modern server-side WebAssembly runtimes. But there are several things that we are missing in the Rust ecosystem. So the first one, as I already mentioned, is stateful procedure markers. So with help of stateful procedure markers, we can simplify our compilation scheme. And by this link, you can provide a discussion. Of course, this feature needed not only to us, yes, but to many other people. And second one is a very minor one. But it's also maybe isn't related to Rust directly, but it's related to Rust ecosystem, to Cargo. And Cargo now transport different build targets for different projects in workspace. For example, in FCE, there is some code that so there is a workspace, yes, and in this workspace there are some projects that should be compiled to native, and some projects that, for example, or tests that should be compiled to WebAssembly. And for example, now it's difficult to achieve the behavior when you type cargo check in the root of your workspace, and all will be checked, all will be, for example, built or tests. So it's minor, but it's very it's features that we are missing in Rust. So on this talk, I presented Fluence Compute Engine and our Rust SDK that could be obtained by these links. And if you have any questions about FCE or Rust SDK or Fluence, you can email me by this address. Also, you can find me in Telegram by this nick. And also, if you want be in touch with Fluence, you can find our email newsletter here, and also you can subscribe to our Twitter. So thank you very much. So if you have any questions, you can write me by email or by this nick in Telegram. So thank you again. Bye.